Physical Sciences session. My name is Temba. Today we are focusing on our attention on understanding the chemical formulae of substances, which is, one of the aspects that has to do with chemical change. So for us to be in a position to actually understand what happens in a chemical reaction, first of all, let's try and create an understanding of the actual substances that take part in chemical reactions. So as a result of that, we shall focus our attention for the purpose of this session on the chemical formulae. Now let's try and locate chemical formulae within the broader, section of quantitative aspects of chemical change, which has to do with reactions, of course. Right. Now, from the concept map, there is our chemical formulae, okay? There is no way that we can talk chemical formulae without making reference to the periodic table of elements, right? Okay, so the periodic table consists of elements. Okay, from these elements we can talk about compounds. Then from compounds we understand the molecular formula in terms of percentage composition as well as empirical formula of the substances that are involved, right? So these are the three aspects that we shall focus our attention for today as part of this session, right? Now, the big thinking question that's going to guide us in our discussion is, have you ever thought about how can we tell what quantity or amount of each element is found in a compound, right? First thing first, let's break it down. What exactly do we mean by a compound? We're talking about a substance that consists of two or more elements of different types that are chemically bonded together. So in terms of composition, we want to understand exactly how each of these elements contribute in terms of mass, in terms of percentage to the entire compound. So the question, that's why it's phrased as, how can we tell what quantity of each element is found in a compound, right? Keywords, very, very important in terms of definitions. Our point of reference then becomes our examination guidelines. Remember to capture the keywords in the correct context. So it's an all or nothing type of an arrangement, and it tests, when it comes to definitions, it has to do a lot to do with our remembering or our basic recall. So we need to remember the keywords. So some of the terms that we'll use once too often in our discussion for today are as follows. We'll talk about the molecular formula. How is it different from empirical formula? So these two are types of formulae that describes compounds or substances, okay? Then we'll talk about percentage composition, cation and anion, amongst a host array of others, but these are the ones that we shall be using once too often than others, right? Okay, now in as far as chemical formulae, from what we already know is that matter consists of particles, and these particles are actually elements. Elements are made up of atoms. But if we zoom our attention to the elements, we talk about the periodic table of elements now, which has a lot to do with the classification of substances or elements that are found in the periodic table. So there are three main categories, okay? We've got metals, metalloids, and non-metals. So metalloids, sometimes we refer to them as semi-metals. Okay, now if we can draw our attention to just the periodic table, at some point we would have maybe looked at the first 20 elements, but in its entirety, the periodic table, this is a typical example of the periodic table as we know it. Okay, so the substances or elements that are listed in the far to our left, this column, which is blue in color, represents the metals, okay? So we've got alkali metals and alkali earth metals, okay? And then in the middle, where we've got these are our transition metals. So anything that we've circled falls under metals, but there are different categories of metals. We've mentioned that groups are actually the vertical columns and periods are actually the horizontal rows. So metals will be further broken down into different categories. And then we've got metalloids, which are actually, semi-metals. These elements, just to mention a few, like silicon, they've got both metallic and non-metallic properties. Hence, we call them metals, metalloids or semi-metals. So the word semi metals, it means they do show some metallic properties, okay? So the word semi-metals and metalloids can be used interchangeably to refer to the same category or classification of elements. And then further to our right, we've got non-metals, okay? These are elements like your bromine, chlorine, you name them. But our focus is not basically it's not actually on the periodic table, but it's on the chemical formulae, okay? So a chemical formula, what does it tell us? It gives us information about the chemical proportions, okay, of atoms making up a substance. A substance could be a compound which consists of, two or more elements that are chemically bonded. It could be a molecule of an element or a compound. So a molecule could either be an element, okay, or it could be a compound, right? You immediately recall that when we talk about molecules, these are covalent substances, okay? We can talk of diatomic molecules like oxygen. We can also talk about compounds which consist of different elements that are chemically bonded together. Or it could be ions. We can talk about ions, a formula of an ion like Na+. We can talk about Br-. These are ions. So formulae, chemical formula can be used to represent any substance, okay? Right. And then furthermore, the chemical formula makes use of symbols, okay? So these symbols, we actually talk about the chemical symbols as we have seen in the previous slide, that when we say Na, we're referring to the sodium ion, Br, the bromine ion, O2, the molecule of oxygen, H2O. So these are the symbols that we use to refer to specific substances, okay? But amongst those, we can talk about numbers. There can be parentheses, dashes, commas, pluses, and minus. For argument's sake, we can talk about ion 3, okay, oxide, okay? Immediately, this is a chemical name, okay? So the 3 is the number that we talk about. But if we talk about the formula, we can also talk about Fe2O3, something like this. So these are the numbers, these subscripts that we talk about, They can be brackets, they can be dashes, just to refer to specific substances. So each element has a unique name as it is reflected in the periodic table of elements. Now, if we focus our attention a little bit on the actual naming of compounds, okay, remember, when we talk of compounds, it means it's now understanding that in the periodic table, there are individual elements. Now, when these elements combine with each other and form compounds, it means these compounds are essentially composed of elements or atoms of different elements that are bonded to each other. Okay, so, but in a compound, these, the constituent elements are reflected in both the chemical formula and name. Say, for argument's sake, we can talk about an ionic compound that consists of two components, which is a cation that is positive and an anion that is negative, okay? So each one of these is derived from an individual element. So in the ionic compound, you'll have both elements represented in the name of that particular compound. So some substances have common names in their actual chemical names. So there are isolated cases where we would have a chemical name as well as a common name. All right, we talk of salt every day. That's a common name. Caustic soda, we talk of lime. These are common names, but these common names are actually related to specific chemical formulae. Okay, so a chemical formula essentially shows the chemical composition and proportion. So the big idea about the chemical name is that it also tells us the composition, or in terms of what elements make up that compound. Okay, so the name in itself, it would be reflective of the names of the elements that make up that particular compound. Okay, take for argument's sake, sodium and chlorine. We talk of sodium chloride. So in that name, it captures the two, constituent elements that make up that particular compound, just as an example. Okay, right. And then let's look at a simple activity like this one, which says, first of all, in the first column, we've got the name. followed by the formula, and then what atoms or elements make up that particular compound. Okay, so carbon dioxide, the formula is CO2. Okay, what does this CO2 tell us? It tells us that this substance consists of carbon as well as oxygen, all right? Now, the dioxide suggests that there are 2 atoms of oxygen and then 1 carbon atom in this formula, right? And then now we've got 2 hydrogen atoms and an oxygen. Okay, in that order we assume. So we've got 2 hydrogen atoms and oxygen. Okay, so the common name for this will definitely be what? Water. Okay, so in that chemical formula, we can immediately pick up that for a formula unit, in this case, a molecule of water consists of 2 atoms of element hydrogen and a single atom of element oxygen. And then we have got the third one, which is ammonia, NH3. So in terms of composition, there is a nitrogen atom. So 1 atom of nitrogen, okay? And in this case, 3 atoms of what? Hydrogen, all right? That's what it says. And then from this formula, we are able to work backwards and actually determine the name of the substance. Okay, this substance consists of 1 copper atom, right? And then 1 sulfur atom, and then 4 oxygen atoms, okay? Right, so the name of the substance is copper sulfate, right? So that's the name, okay? And then calcium hydroxide, okay? The elements that are present here is calcium, hydrogen, and oxygen. So calcium hydroxide, Ca, that's the symbol of the cation, which is positive, which is calcium. And then the hydroxide ion is a polyatomic ion. Okay, then there's a 2 there, okay? We'll discuss as to how exactly we arrive, but our focus is if we are given this chemical formula, we are able to say there is 1 calcium atom, okay? This 2 suggests that it's for everything in brackets, which is for the hydroxide N ion. And then what do we have? 2 oxygen atoms, okay? Right, that's oxygen, all right? And then what else do we have? We've got 2 hydrogen atoms. Okay, so that's the gist in terms of composition, right? Okay, and then in naming ionic compounds, these are some of the rules. The metal cation is derived from some element, okay? And then elements on the left-hand side, will identify them to be, the metals, okay? So these metals, in most cases, they actually form cations, which are actually positive, okay? And then, so when we name these elements, we start with the cation followed by the N ion. So in some cases, there will be terms like mono, meaning 1, di, meaning 2, tri, meaning 3, and so on. So these are some of the common features in naming substances. Then when we talk polyatomic ions, we're talking about ions that have got more than 1 element, and they always consist of the same ratio of elements as a group. Say, for argument's sake, these 3 compounds, ionic compounds, this is sodium sulfate, okay, calcium sulfate, aluminium sulfate. There's something that is very common in these ionic compounds, is that all of them are sulfates, okay? Now, from this, how did you arrive at that? Why are we saying that they are sulfate? Because all of them, they contain this polyatomic N ion. Polyatomic, it means it consists of more than 1 element, okay? So this polyatomic ion, in this case, which is common, is SO4 2 minus, okay? Now, there is SO4 2 minus, SO4 2 minus, SO4 2 minus. So they consist of the same ratio in that for every sulfate N ion, there's 1 sulfur atom and 4 oxygen atoms, okay? And the net charge in that polyatomic ion is 2 minus or -2, whichever way you choose to actually refer to it, right? So when writing the chemical formula of an ionic compound, you start with the cation followed by the N ion. So if we've got that sodium ion and the chloride N ion, Okay, we always start with the metal followed by the non-metal. And the main idea is that at the end of the day, these charges must cancel each other out. So if you realize it's Na plus 1, Cl negative 1. So we can put them in that order, metal, non-metal, then it gives us an ionic compound, as long as the net charge actually cancels out or works out to 0, whichever way you choose to look at it. So this will be just NaCl, and the name sodium chloride suggests that it consists of sodium and chlorine. But take note of the suffix IED, which is the chloride, okay? And then once again, we are given the different ions, okay, below. We want to write down the formula of compounds, okay? These are different cations. These are cations, okay, because they are positive. And then these are anions because they are negative, okay? Right. Now, potassium bromide, okay? That's our potassium anion, bromide. Do the charges cancel out? Yes, of course. So it's KBr, okay? And then calcium bromide, where is calcium? There is calcium, okay? Okay, and then the calcium carbonate, where is the carbonate ion? This is a polyatomic ion, okay? So calcium carbonate, calcium is 2+, and then the carbonate has a charge of 2-. So that works out. So we would remain with CaCO3, okay? So first is the cation, followed by the anion, okay? And then ammonium carbonate, the ammonium ion, there it is, okay? That's our ammonium ion. And then the carbonate is actually 2-, all right? For every carbonate, we must have 2 of these so that it cancels out, okay? So at the end of the day, we'll start with the positive one, which is NH4, okay? We need 2 of those, okay? And then CO3, okay? So that's our ammonium carbonate, okay? Hope that makes sense. And then the last 2, iron 3 oxide. Of particular interest to us is this 3. This suggests something about this transition metal, that it has got a charge of 3+. So this is the ion that we are talking about. So that's the ion 3 that we are talking about. But the oxide is 2-, okay? So in this case, we've got Fe 3+, okay, and O 2-. So for these to cancel each other, we can actually cross them and get Fe, we take the 2 there, and then O, we take the 3 there. So this is iron 3 oxide, okay? In this, there is iron and oxygen. These are the 2 elements in terms of composition. But there is 2, the ratio is 2:3, right? And then last but not least, we've got copper 2 sulfate. That's our copper 2. And then that's our sulfate ion, okay? Now, the 2- cancels out the 2+. What do we have there? We start with the positive according to our rules. We'll say Cu and then SO4. Okay, so that's as far as the main idea. But the chemical formula of an element or a compound, it gives the ratio of moles of each element in the substance. So the main idea is that given the chemical compound or the name suggests the chemical composition in terms of what makes up that compound. But then if you look at the chemical formula, it gives us an idea of the ratio of moles of each element that makes up that compound. Having said that, let's take a short break as we'll continue to explore percentage composition in our second segment. Let's take a short break for now. Welcome back, guys, to our second segment. We're still talking percentage composition. We want to understand chemical formulae. So our focus now, we shall shift it a little bit to focus on percentage composition, to say what percentage of a certain element is present in a compound. This definitely has to be compounds. Why? Because we're talking about different elements forming up a substance, and these elements are actually chemically joined together. Let's locate that. So we are talking percentage composition in as far as chemical formulae. Okay, right. Now the question is, how can you tell what quantity of each element is found in a compound? So we can think of expressing the amount or the quantity of each element in terms of percentages, right? So the answer to that, or the thinking, is that actually the chemical formula gives the ratio of moles. Okay, very, very important. It's the ratio of moles, because quantity of matter is actually in moles, okay? So of elements in a compound. So the chemical formula gives us the ratio of moles of each element in a given compound. So another measure is to express that as a percentage, which has to do with percentage composition, right? Okay, so what exactly is percentage composition all about in as far as compounds are concerned? So the proportion of each element present in a compound can be determined by making use of a chemical formula. So we need to understand the chemical formula, or we need to have the correct chemical formula for us to be able to correctly determine the percentage of each element that makes up a compound, okay? And also we need the relative atomic masses as reflected in the periodic table. So from the name, we've got the chemical formula, and then we can, after that, determine the percentage. Okay, so the mass of each element is expressed as a percentage of the total mass. So it's the percentage of each element based on the total mass of the compound, right? Okay, now the calculation of percentage composition involves the ratio of each element relative to the molar mass of the entire compound. Okay, so when we talk about the molar mass of the entire compound, we are saying these different elements, we look at the correct chemical formula and begin to add. But remember, in some cases, there can be more than one atom, per formula or per molecule of an element. So we also need to take that as well into account. So over and above, we are saying that the percentage of an element in a compound is the ratio of atoms multiplied by the relative atomic mass divided by the molar mass expressed as a percentage. So if the moment you start multiplying by 100, we are actually determining the percentage, okay? Take note of that as well. Okay, here's a question for argument's sake, just to try and drive that point home. It says here, determine the percentage composition of sulfuric acid. So where do we start? We start with the correct chemical formula. Okay, so in this molecule, or this substance of sulfuric acid, we've got 2 hydrogen atoms, okay? These 2 hydrogen atoms, all right? What else? We know that there is 1 sulfur, okay, atom, and there is 4 oxygen atom. So this can only be correct provided the chemical formula is also accurate. So the starting point of determining percentage composition actually starts from identifying the correct chemical formula. So in the first segment, we managed to look at, some of the examples of how exactly we arrive at the correct chemical formula of a given substance, given the name, given the cations and the anions. Now we are able to try, and put together those two so that we come up with the correct chemical formula. Then the chemical formula actually will give us an indication in terms of which elements make up that substance. And then from the subscripts and whatnot, we are able to say, okay, then for this element, there are 2 atoms. For that element, there is X number of atoms. Then this sets the way for us to be able to actually determine the percentage of a given element in a compound, okay? So now the other thing also that is very, very important is the molar mass of that substance. And the molar mass is also derived from the chemical formula. So when we say 2 multiplied by 1, we are saying the atomic mass of hydrogen is 1, but there's 2 of them, hence we multiply by 2. Now each sulfur atom has a mass of 32, okay? Grams per mole. Each oxygen has a mass of 16, but there's 4 of them. So the total, the molar mass of this compound, which is sulfuric acid, is actually 98 grams per mole, okay? Now, so if we were to determine the percentage composition of each of those elements that make up this substance, we've got hydrogen, sulfur, and oxygen. So for hydrogen, we'll say 2 multiplied by 1. 2 in terms of there's 2 of them, but the mass of each one of them is 1, okay, divided by, okay, 98, okay. The 98 here is actually the total, which is 98 grams per mole, okay. If we multiply this by 100, it will actually give us the percentage of hydrogen that is present in sulfuric acid, okay. So if we go to our calculator, what do we have here? We've got 2 divided by 98, okay, multiplied by 100. So we're going to express this as a percentage. So what does that give us? 2,04, okay? So the percentage of hydrogen here is 2,04, right? 2,04%, okay? So this mass of hydrogen expressed as a percentage is 2,04. What about sulfur? Sulfur is actually 38, okay? The molar mass of sulfur, we can just verify it's 32, okay? Just to be correct, we got that from the periodic table, but there's just one sulfur. So it's gonna be 32 over the total, which is 98, multiply that by 100, it will give us the percentage. So if we draw attention to our calculator, okay, we've got 32 divided by 98, okay, multiplied by 100. Okay, this gives us what? The percentage of sulfur, which is 32,65. Always 2 decimal places, okay? 32,65%, okay? And then last but not least, oxygen. Now, if we go back, oxygen, we said 4 of them multiplied by the mass of each one of them, which is 4 multiplied by 16 over 98. We multiply that by 100 because we want to express the mass of oxygen as a percentage, okay? This gives us what? If we go again back to our calculator, we will get 4 multiplied by 16, okay, divided by 98, okay? We'll multiply that by 100, okay? This actually gives us the percentage of oxygen, which is 65,31, right? 65,31%. You can immediately tell that in that 98 grams per mole, a greater proportion is of oxygen. You can even tell from the formula, there is 4 atoms of oxygen, or the ratio is 4, is 2:1:4. So the greater percentage of this molecule or this substance actually is made up of oxygen and some sulfur and very little of hydrogen, because based on its mass, hydrogen is a slightly lighter, atom than the other 2, which is sulfur and oxygen, right? Okay, so that's our percentage composition. Here's another typical example, which is very interesting, okay? It says here, a sample of hydrated copper 2 sulfate, okay? The formula is given, okay? Hydrated, it means that it has got water of crystallization. So if you focus your attention on the inside there, you'd realize that the blue one is the hydrated copper sulfate, okay? So this is our hydrated copper sulfate, okay? So this copper sulfate contains water which has formed those crystals, okay? That's hydrated copper sulfate, copper 2, all right? Okay, so hence this is the formula. It has got water molecules. So the 5, which multiplies the formula of water, is actually the component that represents the water of crystallization. And then on the other end, excuse me, we have got the one that appears white in color. What exactly has happened here? If you burn the hydrated copper sulfate, you actually remove or eliminate the water of crystallization. Then it forms the very same white substance, which is an anhydrous copper sulfate, okay? Anhydrous, it means without water, okay? So this is the white in color, which is copper sulfate, without the water of crystallization. So this other one will be Cu, okay, SO4, okay, but it contains the water of crystallization, while the other one does not, okay? So what is the percentage of water in copper 2 sulfate crystals? Okay, that's what we want to determine. Okay, first of all, we need to be in a position to determine the molar mass of copper sulfate, including the water. And then after that, we are able to determine, to say what percentage of that is actually water, right? So that's what we want to do, right? So the molar mass of hydrated copper sulfate is, so the molar mass of CuSO4, okay, SO4, 5H2O, okay, is, if you go to your periodic table, you'll get 249.69 grams per mole, right? So that's the molar mass. But we want to express the percentage, the water of crystallization, as a percentage of that. So the molar mass of water of crystallization in this case, so it's going to be a molar mass of the 5, this is the pentahydrate H2O, okay? In this case, what do we have? We've got the 5 times 2, okay, all right, plus 5 multiplied by 16, okay? Then what does that give us? Okay, this gives us 5 multiplied by 2, which is a 10, plus, okay, the product of 5 times 16, or 5 and 16, okay, right. So this gives us 90. So the molar mass of this 249.69, 90 grams per mole is actually the water of crystallization, right? So if that's the case, what are we saying? We are saying this is 90 grams per mole, which is the water of crystallization. Then if we want to express that as a percentage, it's obviously going to be 90 divided by 249.69 multiplied by 100. So whatever we get is actually the water of crystallization. Okay, so in this case, we've got 90 divided by 249.69, right? We'll multiply that by 100 so that we get the percentage. The percentage is 36.04, right? So the percentage is actually 36.04%, right? So that's the idea there, okay? And then in a case where we've got nitrogen found in an element such as ammonium nitrate, we want to determine the percentage of nitrogen. We first of all start with the correct formula, which is NH4, the cation ion, okay? Because the nitrate is actually -1, and the ammonium ion is also +1. So there is no need for us to actually have the brackets. So that's the formula. Okay. Now the molar mass of this is actually equals to, so the molar mass of ammonium nitrate, NH4 NO3, is equals to 80 grams per mole. So you'll get this from the periodic table of elements. Okay. Now in this compound, we know that the molar mass is 80 grams per mole, right? And then in this molecular formula, there are 2 atoms of nitrogen, which each one of them has 14. So if we want to calculate the percentage of nitrogen, okay, it's actually equals to 14 multiplied by 2, because there's 2 of them, divided by the total, which is 80 grams per mole, multiplied by 100, okay? So what do we get from that, okay? So if we go to our calculator, we get 14 times 2, which gives us a 28 divided by 80, right? Okay, so we're going to multiply this by 100, which gives us 35%. So what does it mean? It means that 35% of this 80 grams per mole is actually nitrogen. Okay, 35%. Now, what does that tell us? It tells us that in 100 grams, okay, of ammonium nitrate, okay, of NH4, okay, NO3, okay, what are we saying? 35 grams is actually nitrogen, right? Okay, so in every 100 grams of ammonium nitrate, 35 grams is actually nitrogen in terms of percentage composition. So that's the main idea. And now in a 10-gram sample, we know that 35% is actually nitrogen. So to actually find the mass of nitrogen in a 10-gram sample, we'll say, okay, 35 over 100, because for every 100 grams, 35 grams is actually nitrogen. This will multiply by 10, which is the actual mass, okay? So we'll actually get a 3.5 grams, okay, of nitrogen. So what does that tell us? 3.5 grams is actually, 35% of that. So if we are to calculate 35% of 10 grams, we'll actually get 3.5 grams, all right? So that's all about chemical composition, but it also tells us that the chemical formula of an element or compound, it gives the ratio of moles. We've driven that point home of an element that makes up a substance, okay? So in percentage composition gives the ratio of masses, expressed as a percentage, and also percentage composition is a measure of the moles of element for every 100-gram sample. I hope it makes a lot of sense for now. Let's take a short breather. When we come back in our third and final segment, we'll take a look at the empirical formula. Let's take a short break for now. Welcome back to our third and final segment. We're still looking into the quantitative aspects of chemical change, but now we shall focus our attention on the empirical formula. Right, so now we understand the chemical formula. We also understand percentage composition in terms of elements making up, a compound, and this is has to do with the mole ratio. But now we want to focus our attention on the empirical formula, right? Okay, what's empirical formula all about? So the empirical formula of a compound, it's always about a compound. It means it should be more two or more different types of elements that are chemically joined. So the empirical formula of a compound actually shows the simplest mole ratio. So those are the key terms. It's the simplest mole ratio in which elements of a compound have bonded. So our emphasis is on the mole ratio in its simplest form. Okay, so these substances' actual molecular formula could be multiples of each empirical formula. So if we get the simplest whole mole ratio of each element that is in a compound, if you double it or treble it, it could in some cases give us the actual molecular formula of the substance. So the empirical formula of a compound can be calculated from its percentage composition, right? So percentage composition, something that we know, we're expressing the mass of each element as a percentage of the total mass of the compound, right? And then what are the steps that we have to go through in terms of determining the molecular formula? Okay, first of all, express the percentages of each element in terms of a 100-gram sample. So for argument's sake, if we say a substance is 35%, it means for every 100-gram sample, that element is a mass or contributes a mass of 35 grams. Okay, so we convert the mass of each element to the number of moles, okay, because it's always about the moles. Because remember, the empirical formula shows the simplest whole number ratio of moles of each element. So at the end of the day, we must determine the moles, right? Okay, then we can simplify because this is the simplest whole number. And when we talk about whole number, we're talking about integers. I think you recall that very well. Here is a typical example with a compound that is made of 36.5% sodium, okay? Right? We also have 25.4% of sulfur, and then 38.1% of oxygen. Then we want to determine the empirical formula of this compound. Now, before we even do all the complex calculations, let's think about this way. Are we able to guess the chemical formula that could be between, because it contains sodium, sulfur, and oxygen in that order? We shall maintain that order. So we've got sodium sulfite and sodium sulfate. Okay, now if you look at the percentage by mass, let's say for argument's sake, compare sodium to oxygen. You know, in the sulfate, it's 2:4 for sodium to oxygen ratio, while in the sulfite is 2:3. So this is a sulfite, okay? This is a sulfite, and then this is a sulfate of sodium, okay? Okay, that's the difference. So the difference lies in the complex polyatomic ion there. Okay, so you just check that the oxygen is 38,1 while sodium is 36. So these two are much more comparable. Why in the sulfate is almost double. So let's think about that in terms of predictions. Okay, now if we are to do the actual calculations, so of this sodium, let's simplify the mole ratio of sodium. So 36.5% is sodium. Let's express this as a percentage, right? Now let's determine the mole ratio of each of these substances. So if 36.5% is the percentage composition of sodium in the compound, it means for every 100 gram sample, 36.5 grams is actually sodium. So we are simply saying that 36.5 grams, which is for 100 gram sample, divided by the molar mass of sodium, which is 23 grams per mole, okay? While for sulfur, it's going to be 25.4 grams, okay, per every 100 gram sample, divided by the mass of sulfur, which is 32 grams for every mole, right? And then for oxygen, we've got 38.1 grams for every 100 gram sample, divided by the molar mass of oxygen, which is 16 grams per mole, right? So what we get in each of these calculations is actually the mole in terms of each element, okay? So if we go to our calculator, we will get 36.5 divided by 23, okay? That gives us, okay, 36.5, just to 36.5, okay, divided by 23, okay? What do we get? This gives us, as a decimal fraction, 1.59, okay? Okay, 1.59 mole, okay, right? And then if we go to the second one, what do we get? 25.4, okay, divided by 32, okay? What do we get as a decimal fraction, 2 decimal places? Okay, this is 0.79, okay, right. Just to go back to that, 0.79 mole, right? And then the last one for oxygen, what do we have? We have 38.1, okay? We divide that by the molar mass of oxygen, which is 16 grams per mole. That expressed as a decimal fraction is 2.38, right? So that is 2.38 moles, right? Now, if we are to express the ratio in terms of sodium is to sulfur is to oxygen, in the and we want to simplify the mole ratio, we have got 1.59, right, is to 0.79 is to 2.38, okay? So now we want to simplify this because we want to get the empirical formula. So we'll definitely divide, let's say, by 0.79 throughout, okay? All right, 0.79 divided by 0.79, right? Okay, so if we go back to our calculator, we will have, obviously, this will give us a 1, but we'll do the 1.59, okay? 1.59 divided by 0.79, okay? This gives us a number 2, okay? We'll get a 2 there, right? So this is a 2 is to 1, okay? Is 2, let's simplify the other end, which is 2.38, okay? 2.38 divided by 0.79. This gives us a what? We'll go back to, this gives us a 3, all right? So this gives us a 3. So the ratio of sodium is to sulfur is to oxygen, in the simplest whole number ratio is going to be sodium 2, and then 1 atom of sulfur, 1 mole of sulfur, and then 3 moles of oxygen. So this is our empirical formula. So the substance in this case is going to be our sodium sulfate. Now, what's the long and short of this? These are the different steps that we carried out in terms of determining the empirical formula. So at the end of the day, we want to appreciate that the chemical formula of an element or a compound, it gives us the ratio of moles. It's always about the moles of each element that is present in a substance, which in most cases is actually a compound. And then the percentage composition actually gives us the percentage ratio of the masses of each substance. And then the last that we did, the percentage composition, is a measure of the moles of each element present in a 100-gram sample, because we want to express this as a percentage, right? So those are the main ideas. And then the empirical formula, okay, it gives us the simplest whole number ratio of moles. It's always about the moles, okay, of each element that is present. Now, and then the molecular formula is the actual formula of the substance is a chemical formula that gives us the exact, which is the actual whole number ratio that makes up a molecule. So these are the different types of formulae in terms of the percentage composition. We also looked at the masses. So there's a whole range, you know, of ideas that we managed to discuss in terms of percentage composition, molecular formula, as well as empirical formula. I certainly hope that makes a lot of sense when it all comes together. So that's the time that we have for today in terms of, you know, the quantitative aspects of chemical change. For now, it's cheers and bye-bye for now.